This time we're taking a look at section 16.3. And this deals with the fundamental theorem for line integrals. And we're going to start with this theorem. And here we're going to have C as a smooth curve. That's going to be given by the vector function R of t, where t ranges from A to B. And then we're going to let f be a differentiable function of 2 or 3 variables. And f is going to be such that its gradient vector is continuous on this curve C. So we'll be taking a look at the line integral of gradient of f along C. And that's going to be equal to f of R of B minus f of R of A. So what we're getting from this is that we can evaluate the line integral of a conservative vector field by knowing the endpoints, or the value of the function at the endpoints of the curve C. So let's take a look at a situation in which we're dealing with a function of 3 variables. So let's let f be a function of 3 variables, and let's let C be a curve in space. Joins the point A with coordinates x1, y1, and z1 to the point B. With coordinates x2, y2, and z2. Then what's going to happen is take our line integral gradient of f along C. That's going to be the same thing as f of x2, y2, z2 minus f of x1, y1, z1. So basically what this theorem is telling us is that if we were to take the terminal point of this curve and basically plug it into our function f, subtract away what we got when we plugged the initial point into f, and that's going to be the value of our line integral gradient f along C. Now let's take a look as to why this would be the case. Now if you take a look at line integral of gradient of f along C, what you notice is that this is the same thing as the integral from A to B. Gradient of f of R of t dotted with R prime of t dt. But if you think about what the components of gradient of f look like, you've got partial f with respect to x, partial f with respect to y, and partial f with respect to z. Well, your components of R prime will be derivative x with respect to t, derivative y with respect to t, and derivative z with respect to t. So so what this turns into is integral from a to b. Now if we take a look at multiplying the first components together, partial f with respect to x from here, derivative of x with respect to t from here. Then you add the product of the second components, so you're adding partial f with respect to y times derivative of y with respect to t. Then you'll add the product of the third components, which will be partial f with respect to z times derivative of z with respect to t. However, if you take a close look at what we have in parentheses here, this is really the same thing as the derivative with respect to t of f of r of t. So this is the integral from a to b, derivative with respect to t, f of r of t dt. Which, of course, is the same thing as f of r of b minus f of r of a. And so when you take a look at this, that's the left side of the equation in this theorem. Well, this is the right side, so this gives a bit of an indication as to why this equation works the way it does. Now, the next thing we're going to be taking a look at is something called independence of path. And so here we're going to let C1 and C2 be a couple of piecewise smooth curves. Called paths. And these are going to have the same initial points and same terminal points. And so maybe we'll say same initial point A, and let's give these names. Same initial point A and same terminal point B. Okay. So one of the things we saw in the previous section is that in general, if you take the line integral of f along C1, it's not going to, in general, be the same as the line integral of f along C2. In fact, we did an example in the previous section in which we had two paths, same initial points, same terminal points, but we ended up getting two completely different answers for the line integral based on the path. However, one implication of this previous theorem is that if we take the line integral of the gradient of f along C1, that is going to be the same as the line integral of gradient of f along C2, because the terminal points and initial points are going to match up among the two paths. So basically what we get is following. Line integral gradient of f along C1, line integral gradient of f along C2, whenever the gradient of f is continuous. So that's one of the conditions of the theorem here. And so what this means is that the line integral of a conservative vector field really just depends on the initial point and the terminal point of the curve. Once again, line integral of a conservative vector field depends only on the initial point and the terminal point of the curve. All right. So with that, let's take a look at the following definition. So for this definition, we have if f is a continuous vector field with domain D, then the line integral we'll have the line integral of f along C. This is independent of path. If the line integral of f along C1 is equal to the line integral of f along C2 for any two paths, C1 and C2, that have the same initial points and the same terminal points. Alright, so once again, f is a continuous vector field, domain D. We say that the line integral of f along C is independent of path. If for any two paths C1 and C2 in D that you choose, the line integral of f along C1 will equal the line integral of f along C2, as long as those two paths have the same initial points and the same terminal points. Alright. Now, I've got one more definition that I need to show you before we get to the next theorem. And we say that a curve is called closed if its terminal point coincides with its initial point. Now, the terminal point coincides with the initial point, and what that means is that if you have R of t representing the curve, C, then R of B is equal to R of A. And so, once we have these definitions, we're ready to jump into the next theorem. And that theorem goes something like this. So we're going to be taking a look at the line integral of f along C. So that line integral of f along C is independent of path in D. If and only if the line integral of f along C is equal to 0, whenever you have a closed path C in D. All right. Now we have one more definition you need to take a look at. And this definition of a connected region. So we say that a region D is connected if any 2 points in D can be joined by a path that is entirely in D. All right. So we're going to suppose that F is a vector field. That is continuous on an open connected region D. So if line integral of f along C is independent of path, in D, then f is a conservative vector field in D. So what that means is that there's going to be a function little f such that big F is the gradient of little f. Okay, so let's try to get an idea as to why this is true. Okay, so we'll have some sort of open connected region D, and maybe this region looks something like this. We're also going to have, let's say, some point that we're going to call A, and this will be a fixed point right here. So that's going to be our point A. And let's say that it has coordinates little a and little b. And once again, this will be our open connected region D. And we're going to define a function f, little f, and little f is going to be equal to this integral here. See, we're going to have a path that has initial point A and terminal point we're going to call xy. And so we're going to take the line integral of f from the point AB to the point xy. And this is going to be true for any point xy that's in the region D. And so maybe our point xy is somewhere around there. So let's just choose that as an arbitrary point. Xy is in D. All right. And once again, we have this function little f of xy that's defined in this way. Now, what you have to keep in mind is that according to the assumptions in the theorem, the line integral of f along c is independent of path. So it really doesn't matter how we get from this point A to this point xy. We can get there any way we want. The value of the line integral is still going to be the same regardless. And so we rely on the fact that this region D is open, and that means that we're going to have some sort of disk that's centered at xy that's going to be completely contained in the region D. So let's say that's our disk that's centered at xy. Once again, it's going to be completely contained in D. There's definitely going to exist some sort of disk like this. And then what we're going to do is we're going to choose a point that's somewhere to the left of this xy, but still within this disk that we've just drawn. And so let's think about maybe, let's go ahead and maybe put that point right here. Now this point is going to be at the same y coordinate that the xy is, but the x coordinate is going to be a little bit less than x. So what we're going to do is we're going to call this point, let's go ahead and call that x1, y. And then we're going to look at some sort of path that is going to go from A to this point here, but it's going to consist of two different pieces. We're going to have some path C1 that takes us from the point A to this point that we've just put up. So maybe that looks something like this, and that'll be our path C1. They're going to have another path C2 that's going to go from this point x1, y to xy. All right, so let's think about what our f of xy will look like in that case. Well, the f of xy would actually be the sum of two line integrals. So you'd have the line integral of f along C1 plus the line integral of f along C2. Once again, we're going to get the same value no matter which way we get from this point A to this point xy. Now, if you think about it though, if we take the line integral of f along C1, now this is going to be the same thing as the integral. Let's make a little room here. So let's get our little f of xy. Well, once again, this line integral of f along C1, you're going to have well, keep in mind what C1 looks like. C1 is going to take us from this point A to this point with coordinates x1, comma y. And so if you think about the integral, line integral of f along C1, basically what you would get is this representation just with an x1 here for that x coordinate up top. So but then we'd also have to add to this the line integral of f along C2. Now, let's think about this for a moment, though, because if you take a look at this very first integral here, what you'll realize is that it doesn't depend on x. And so if we take a look at the partial derivative of f of xy with respect to x, then what we're going to get from this first case is just going to be 0. And then plus the partial derivative of this thing with respect to x. Now, let's suppose that f is equal to some pi plus qj. Now, if f is equal to pi plus qj, then one thing we know is that this line integral of f along C2 is going to be the same thing as the line integral of p dx plus q dy along C2. Something we saw in the previous section. Now, think about C2 for a moment. If you take a look at C2, what you'll notice is that y isn't changing at all. And so that means that our differential of y is going to be 0. And if the differential of y is equal to 0, then the q dy is going to be 0. So what you actually would have is the line integral of p dx along C2. So if we use t as a parameter, introduce this parameter t, and basically it's going to range from x1 to x. So range from the x coordinate of this point to the x coordinate of our sort of destination point. So use t as a parameter where t ranges from x1 to x. What we're going to get is the following. Get the partial derivative of f of xy with respect to x is going to be the same thing as the partial with respect to x. line integral p dx plus q dy along C2, but remember, as I said before, dy is equal to 0. And another way that we could write that is we could say that this is the partial with respect to x of the integral from x1 to x of p of t comma y dx. All right, sorry, p of t comma y dt. Sorry about that, it should be a dt. But then, if you use fundamental theorem of calculus, what you would get is that really this is just the same thing. You've got the partial with respect to x of the integral from x1 to x of p of ty dt. All we have to do is plug in the x for t, and we have our result. And so this will be the same thing as p of x comma y. Now let's think about what that means. Think about what that means. What it means is that the partial derivative of this little f with respect to x is our p of xy, which is the first component of our big F. Now, in a similar fashion, we can show that the partial with respect to y of f of xy is equal to q of xy. Basically, do the same type of argument, but instead of taking an x1 comma y here, you would take an x comma y1 here and then move up for your C2. So you'd have a path C1 that would take you to a point down here, and then C2 would take you from that point up to C2. So in a similar fashion, partial of the f of xy with respect to y is equal to q of xy. So if you think about the fact that f is pi plus qj, then what you actually get is that f is going to be partial little f with respect to x times I plus partial little f with respect to y times j, but that's just the gradient of little f. So big F is the gradient of little f, which means that big F is a conservative vector field. All right, so at this point we're going to have a theorem, two more definitions, another theorem, and then finally we'll be able to get into some examples. So for this theorem, let's suppose we have f of xy is equal to p of xy times I plus q of xy times j. And let's say that that's a conservative vector field. And let's say that p and q have continuous first order partial derivatives on a domain D. Then throughout D, going to have is that the partial derivative of p with respect to y is the same as partial derivative of q with respect to x. All right. So now let's take a look at a couple of definitions here. So for this definition, we have a simple curve. And a simple curve is a curve that doesn't intersect itself anywhere between its endpoints. And their next definition is that of a simply connected region. So a simply connected region in the plane is a connected region D, such that every simple closed curve in D encloses only points that are in D. So if you were to have some sort of region D like this, this would be a simply connected region, because if you have any sort of simple closed curve in here, you're only going to be enclosing points that are in D. But if you have a region like this, let's say, where this is D, I could have some sort of simple closed curve like this, and it's going to include points that are not in the region D. So this would not be a simply connected region. So we have one more theorem and then we're ready for some examples. And so for this theorem, we're going to have f is pi plus qj. And this is going to be a vector field on an open, simply connected region D. And let's suppose that P and Q have continuous first order partial derivatives. So once again, P and Q have continuous first order partial derivatives. And partial of P with respect to y is equal to the partial of Q with respect to x throughout D. if that's the case, then f is conservative. All right, so once again, f is a vector field, open, simply connected region D. Component is p and q, have continuous first order partial derivatives, and partial p with respect to y equals partial q with respect to x throughout D. And f is a conservative vector field. So let's take a look at some examples. And in this example, we're going to determine whether or not a certain vector field is conservative. So once again, determine whether or not the vector field f of xy equals, and so our component functions are going to be x minus y and x minus 2. So we'll have an x minus y I plus an x minus 2 j, and so we're going to determine whether or not that vector field is conservative. Well, what we're going to need to do is recognize that p of xy is x minus y, and q of xy is x minus 2. But when we go to take a look at the partial of p with respect to y, what we're going to get is a negative 1. And if we take a look at the partial of q with respect to x, what we're going to get here is positive 1. So it turns out that these partial derivatives are not equal, which means f isn't conservative. Alright, so once again, partial derivatives here were not equal, so yeah, f is not a conservative vector field. But let's take a look at another example. And so in this case, we're going to have f of xy equals 3 plus 2xy times I plus x squared minus 3y squared times j. So we'll determine whether or not that's conservative. Well, in this case, notice that we have our p of xy is 3 plus 2xy. And we have our q of xy is x squared minus 3y squared. So we go to take our partial p with respect to y, and when we do that, well, 3 differentiates to 0, and then x gets treated as a constant, so we have a constant multiple times y. Take the partial p with respect to y, you just get that constant multiple, which is 2x. Now if we take the partial of q with respect to x, this x squared differentiates to a 2x, and the negative 3y squared differentiates to 0 because, well, y is treated as a constant in that instance. So notice that what you have is partial p with respect to y is partial q with respect to x. But also, if you think about the first part of this theorem, what you'll notice is that the domain of our vector field is the entire plane. And that's definitely open and simply connected. So f is conservative. All right. Now, let's also consider the following. Let's say in part A, we're going to have f of xy. Well, it's going to be the same vector field we saw in the previous example. So we have the 3 plus 2xy is I, plus x squared minus 3y squared times j. So if f is defined this way, then we're going to find a function little f such that big F is the gradient of little f. Now we know that such a little f exists because in the previous example we showed that big F is conservative. And then in part B, we're going to evaluate the line integral. So I have the line integral of f along C, where C is the curve. And that's given by, and we'll have an r of t is equal to e to the t sine t I plus e to the t cosine t j. And we're going to have t ranging from 0 to pi. Now let's set our attention to part A. Once again, we have big F of xy is 3 plus 2xyi plus x squared minus 3y squared j. So if we think about it, what this tells us is that this 3 plus 2xy is actually the partial derivative of little f with respect to x. And so if we want to get a basic form for little f, then what we can do is we can integrate this thing with respect to x. And we'll get a basic form for f of xy. If you integrate the 3, you would get 3x. Integrate the 2xy, you get an x squared y. And then you might say, and then you get a plus c for a constant, but that's not entirely the case. While we do expect to have a plus a constant, what you have to keep in mind is that any function of y is going to be considered to be a constant. So instead of adding just a plus c, we're going to have to add some sort of g of y. So that's going to be sort of a general form for our f of xy. Now, from here, we're going to need to figure out something about the partial of f with respect to y. And we can do that in two different ways. Number one, we can take the partial of this thing with respect to y directly, but we also know that the partial of f with respect to y is the component function here for j. And so, first off, let's take the partial of f with respect to y directly here. What we'll get is partial f with respect to y is equal to, well, 3x is treated as a constant, it differentiates to 0. X squared y would differentiate to x squared, and then the g of y would differentiate to g prime of y. But there is more to the story. A lot of times in mathematics, it's really helpful to express the same thing in more than one way. Sometimes you can get some really useful information. And so, once again, we know that partial of f with respect to y is equal to our component function here. And so that's going to be our x squared minus 3y squared. Now, if partial f with respect to y is equal to this, and it's also equal to that, then that means that this expression is equal to that expression. So we're going to have x squared plus g prime of y is x squared minus 3y squared, which then leads us to the conclusion that g prime of y is a negative 3y squared because the x squares are just going to cancel here. Well, if you want to get g of y, which presumably you do so you can get a better idea of what f of xy looks like, then go ahead and integrate the negative 3y squared, and then you'd have a g of y is negative y cubed plus a constant that we're going to call k. So once you have this representation for g of y, you can then take that, plug it in here, and that'll tell you what your f of xy is. And so we'll have our function little f is going to be the same thing as a 3x plus xy squared minus y cubed plus k. All right, so that handles part A of the example, but there's also the part B where we're being asked to evaluate the line integral of f along C, where C is given by this curve here. And so what we're going to need to do is figure out, well, what are the initial points and the terminal points of C? Because from the theorem from the very beginning of the section, if we know the initial points and the terminal points of C, then we can plug those into our function f to produce the result of this line integral of f along C. Alright, so if we want to get the initial point of C, then what we're going to need to do is plug in 0 for t here. Alright, so initial point, we'll have r of 0. And so you're going to get an e to the 0 times sine 0. Your first component, and e to the 0 cosine 0 is your second component. And so we know that r of 0, e to the 0 gives you 1, sine 0 is equal to 0, cosine 0 is equal to 1. So our initial point is 0, 1. Now we also have to figure out the terminal point. And for the terminal point, well, remember that t ranges from 0 to pi, so we're going to find r of pi here. So we'll have e to the pi times sine pi is our first component, and e to the pi times cosine pi is our second component. Now keep in mind that the sine of pi is equal to 0, while the cosine pi is equal to -1. So you have e to the pi times 0 for your first component, e to the pi times -1 is your second component. So that means that our terminal point is at 0, negative e to the pi. All right. Now, according to the initial theorem that we had in this section, if we're going to evaluate this line integral, f along c, we know that's going to be equal to little f evaluated at the terminal point minus little f evaluated at the initial point. And so we start to think about, well, what is that actually going to work out to be? And if you take a look at how our f is defined at the end of part A, if we take a look at f of 0, negative e to the pi, remember x is 0, y is negative e to the pi. So you're going to get 3 times 0 plus 0 squared times negative e to the pi minus negative e to the pi raised to the third power. Now, we're not going to have to worry about the plus k here, because if you included the plus k with the f of 0, negative e to the pi, and also included it with the f of 0, 1, those k's would end up just canceling each other out because of the difference here. And so what we get is that a lot of the zeros out, but if you take negative e to the pi raised to the third power, that's going to be negative e to the 3 pi. Preceded by the negative sign here, you get e to the 3 pi. And then if you take a look at f of 0, 1, once again, x is 0, but y is 1 in this case, so you'll have a 3 times 0 plus 0 squared times 1 minus a 1 cubed, and that's just going to give us -1. So it turns out that this integral is e to the 3 pi minus a -1, or e to the 3 pi plus 1. So we have one more example to take a look at. And this time we're going to be taking a look at f of x, y, z. And we're going to define that as y squared I plus 2xy plus 3z, plus 2xy plus e to the 3z times j plus 3y e to the 3zk. And let's take another line to do this. So let's start way over here. And once again, we'll have f of x, y, z is equal to, we're starting out with the y squared I. Then we'll have a plus 2xy plus e to the 3z j. And then our k component is 3y e to the 3z. So if our vector field is defined this way, then we're going to find a function, little f, such that big F is the gradient of little f. Now, if such a function exists, then we're going to need the partial of little f with respect to x to be y squared, partial of little f with respect to y to be 2xy plus e to the 3z, and partial of little f with respect to z will need to be 3y times e to the 3z. And so if that's the case, what we can do is try to get sort of a general form for this little f. So if you think about the fact that partial little f with respect to x would need to be equal to y squared, and if you were to try to find some sort of little f of x, y, z, then what you'd want to do is integrate this thing with respect to x. But you have to keep in mind that there are two other variables involved, namely y and z. And so if I integrate this thing with respect to x, I will get an xy squared. And much like before, I'm not going to just put a constant here. I'm going to have to put some function. Now, last time we had our constant as a function of y. This time we're going to have to think of our constant as a function of y and z. Because if you take any sort of g of x, or sorry, any sort of g of yz, you take the partial of that thing with respect to x, this is going to zero out. And so our f of x, y, z we can think of as xy squared plus some sort of g of yz. Now, in much the same way as before, we're going to need to know something about the partial of f with respect to y. And so we can think about the partial of f with respect to y in a couple of ways. We can get it by taking the partial of this expression directly with respect to y. And we can also think about the fact that we're going to need partial f with respect to y to be equal to that component function for j. And so if we think about partial f with respect to y, first part you're going to get a 2xy. And the second part you're going to get the partial of g of yz with respect to y. Now, we know that this is also supposed to equal 2xy plus e to the 3z. And so if both of these expressions are equal to partial f with respect to y, we can set them equal to each other. When we do that, the 2xy's are going to cancel out. You'll have the partial of g of yz with respect to y is equal to e to the 3z. And so we think about, well, what does that tell us about g of yz? Well, what it tells us is that g of yz, if you integrate with respect to y, you're going to get a y e to the 3z plus some sort of constant we're going to call h of z. Because remember, if we take the partial of this thing with respect to y, the h of z differentiates to 0. And so now we have a little bit more information. We now know that this f of xyz is going to be xy squared plus g of yz, where g of yz is y e to the 3z plus h of z. So we can go ahead and modify that f. And we're almost there, because now what we have to do is figure out what this h of z is. So we can think about directly finding the partial of f with respect to z here. And we take the partial of f with respect to z. Remember, x and y are treated as constants. So this xy squared is going to differentiate to 0. The y e to the 3z, well, y is going to be a constant multiple. But you differentiate the e to the 3z, chain rule comes into play, and you'll get a 3e to the 3z from that. So differentiate the y e to the 3z with respect to z, you get a 3y e to the 3z, and then differentiate the h of z, and that's h prime of z. So that's one way to represent your partial of f with respect to z, but we said earlier that partial f with respect to z would also have to be the component function for k, which is 3y e to the 3z. So at this point, we have two different representations for the partial of f with respect to z. And because of that, we can set those representations equal to each other. And so 3y e to the 3z plus h prime of z is equal to 3y e to the 3z. Now what you may notice from this is that the 3y e to the 3z terms are going to cancel out, and what you'll have is h prime of z is equal to 0. Now if h prime of z is equal to 0, that means h is equal to some constant k. And so now we can go to this representation we had most recently for f. We can plug in k for h of z, and that gives us f of xyz is equal to xy squared plus y e to the 3z plus k. And that is our final answer. And with that, our last example is finished, which means the section is finished. And I do have some recommended exercises for this section. And those recommended exercises are 3, 5, 7, 15, and 23.